All right, this video is just going to introduce you into systems of linear first-order differential equations. And so the way in which this is going to work is we are going to write our linear systems in normal form. What that means is you have your derivative in the front, and then you have all of your other terms back behind, and you do potentially have a function if this is a non-homogeneous situation that you might have here in the back. So when all of these functions here in the back are equal to 0, then you're going to have a homogeneous solution. If they are not 0, then you have a non-homogeneous solution, and we'll look at an example of that today. The matrix form of a linear system is an easier way to write a system of equations. So when you're trying to figure out a solution, maybe like an x1 to xn, we're going to go up to x, y, and z in this situation, but you could go up to like an nth dimension. It's easiest to then write in this form. So you have all of your coefficients in a matrix, and then you say plus this f of t on the end. And so this is how we're going to end up writing this. So you take the derivative, like x prime, if you will, of that first vector, and you're going to set it equal to all of the coefficients of that original function here. So if you look, all these coefficients here times their x's, and then plus f of t. Let's go ahead and write maybe that first example so you can see how this would work to go back and forth, just in case you're not quite sure how matrix algebra works. So what this first row would be is x1 prime is then equal to, and then you multiply that first row column input by x1. And then the second one by x2, and then you keep doing that so on and so forth until you get to that nth one times xn. And then if we do have a non-homogeneous situation, then you'd have plus f1t. And that's going to go all the way down to that like nth dimension, like we said. So everything that we've done so far has just been like one of these. And now we're talking about like, what if you have an entire system? Like, what does that look like where they're all dependent on each other? In this problem, again, in our problems that we work with in this class, we're only going to go x, y, z, but you could essentially with linear algebra go up to the nth dimension. All right, so let's look at how to do this just in x, y. So how we do this, we say like, okay, big X is then going to be the vector x, y. And so x prime, which is little x prime, y prime, is then equal to a x. So in this specific example, our a is going to be the coefficients in front of x and y, and then times x. And if you want to see, again, just in case maybe matrix algebra isn't something you've done, how you would then write this is 3x plus 4y, and then 5x minus 7y is how that matrix algebra works. Okay, all right, let's look at a 3-dimension example. So in this case, I'm going to let x be equal to x, y, and z. And so I can just say x prime is then 6, 1, 1, 8, 7, negative 1, 2, 9, negative 1 times x. And then notice this is a non-homogeneous situation here. So plus t, 10t, 6t on the end. All right, let's keep talking about solutions. So if I want to verify that these are solutions to this differential equation, how we would do that is I would need to just show that x1 prime is equal to this here, with this being my x. All right, well, x1 prime would be -2 e to the -2. You just take the derivative piecewise here, and then 2 e to the -2. And I want to verify that that's equal to this times my x. So e to the -2t plus -3 e to the -2t, and 5e to the -2t plus -3 e to the -2t gives me -2 e to the -2t, and then 2 e to the -2t. So that is a solution to this system here. We can do that exact same thing for x2 prime, making sure that it's, I guess I should have put an x1 there, but that's okay. All right, so its derivative would be 18 e to the 6t and 30 e to the 6t. And I want to show that this is equal to a times x. So that's going to be 3e to the 6t plus 15e to the 6t. On the bottom, 15e to the 6t plus 15e to the 6t. And that's equal there. So those are both solutions. We can show that they are linearly independent solutions using the Wronskian. So that first solution is e to the -2t, -2t, 3e to the 6t, 5e to the 6t. So that's going to be 5e to the 4t minus -3e to the 4t. These are e functions, so they're never zero, so they are linearly independent. And then just like we did before, when we had differential equations, we can then write a fundamental solution set. So what does that mean? That means that big X or xy must be equal to some C1 times this piece right here. So let's write it in vector form, actually. E to the -2t plus C2 times 3, 5 e to the 6t. And so that's how we're going to be writing our solutions to this differential equation, where x of t is then c1 e to the -2t plus 3c2 e to the 6t. And since it's a system, it does matter that this is 3c2, because I'm going to have a c2 over here, so -c1. So I know sometimes we be like, oh, well, that just like absorbs it or whatever. Since there is a C1 and a C2 in this system, then those need to stay as those multiples. So that's what it means. So these are parametrics. If you did that like in your Cal 2, these are parametric equations. Right, so x is moving in this, x of t is moving in this direction, y of t is moving in this direction. And so you'd have an entire like phase portrait that you could look at depending on like which direction you are looking at for these two functions here. All right, so then here is our theorem as to like what we can do for writing these general solutions, right? So we did that right here, you end up writing your complementary function by taking those constants and multiplying by each one of their solution vectors. And then if you do have a non-homogeneous solution, then you would add that xp on the end. So let's go ahead and show that this is a solution to a non-homogeneous system. Notice here that this first part is the problem that we just did here. Okay, so I already know this solution that I found here is like my xc. So c1, 1, negative 1, e to the negative 2t. c2, 3, 5, e to the 6t. So now I need to find this xp. So I'm just showing, it's like showing you like this is what it is, just verify that it's the solution. So what would be xp prime? It would be 3, negative 5, right? So let's go ahead and show that 1, 3, 5, 3 times xp would be plus, right, plus this, that those are equal to each other. Well, let's see, is 3 equal to 1 times this plus 3 times that second piece plus 12 here? So is 3 equal to 3t minus 4 minus 15t, 3 times this, minus 15t plus 18 plus 12t minus 11. These all cancel. And when I combine this, I do get 3. Yay! All right, negative 5, is that equal to 5 times 3t minus 4 plus 3 times negative 5t plus 6 plus negative 3. So is negative 5 equal to 15t minus 20 minus 15t plus 18 minus 3. These cancel, and I end up getting that that is the solution. So then how I write the full solution of this is I would write x is then equal to c1, 1, negative 1, e to the negative 2t, plus c2, 3, 5, e to the 6t, plus this right here. So that's plus your f of your ft. So 3t minus 4 minus 5t plus 6. And that's going to be my full solution. Again, you can write this as like, so x of t is c1 e to the negative 2t plus 3c2 e to the 6t plus 3t minus 4. And I'm going to write my solution for y like so.